What's up, guys? Another video on structure and bonding. Again, this video is probably more GCSE revision than anything else. We'll get onto the more complex stuff a little bit later on. For now, like, subscribe, share with anyone you think would be interested. I want to grow this channel so much as possible. Let's get into it. Covalent bonding. Basic definition: we've got a shared pair of electrons here, right? And at GCSE we talk about between non-metals. That's not necessarily the case at A level, so we won't say that, right? We won't get into that too much. But we can sort of start to, again, label our periodic table. So really we're talking about the stuff around here where covalent bond mostly happens. Other things, we're going to have things called dative covalent bonds, but we'll worry about that further down the line. So working from group 7, you know, this isn't strictly true, but let's say on average they're mostly going to have 7 electrons in the outer shell. We know that's not entirely true once we get down here, but for simplification, let's go. They need 1 more electron in order to get a full outer shell. So because they need 1 electron, they're only going to form 1 covalent bond. Oxygen, we know, is going to have 6 electrons in the outer shell. It only needs 2 more electrons, so it's going to form 2 covalent bonds. Nitrogen, 5 electrons in the outer shell. It needs 3 more electrons, so it's going to form 3 covalent bonds. Carbon, 4, etc. Hydrogen, remember period 1 only requires 2 electrons in that first energy level, so only 1 covalent bond can be formed to give it that full outer shell. So let's do some examples. Now we've got 2 types of diagrams that we're going to draw today. We've got just stick diagrams. You'd have known them at GCSE. Now we're going to call them displayed formula. And then we've also got our dots and cross diagrams, which we'll draw underneath here. So hydrogen we just labelled only requires 1 electron to get a full outer shell. So we can draw like so. Now this represents a single covalent bond, so a single shared pair of electrons. All right, so as we move over to our dot and cross diagram, we're going to replace that single line with our dots and cross and fill in our hydrogen. Then we just double check. Here we're only going to tend to fill out the outer shells of electrons. We don't want to worry about the inside shells. Obviously that doesn't apply to hydrogen, but it applies to other things. We just need to double check. Okay, we've got our 1 electron in the outer shell. We're good. Next. Carbon, group 4, 4 covalent bonds needed. That ties quite well with our ratio here, right? So and again, each of those basically represents a covalent bond. So we sort of copy the shape and we replace those lines with our dots and crosses. Perfect. And it's worth saying, let me change this one actually. So let's change this one for CL4, and instead we'll have CLs dotted around here. And again, this would still work. It's in group 7, so it only requires 1 extra electron. But we need to adjust here. Because at that point, the outer shell won't have just these electrons, it will also have the rest completing. So we'll need to draw the rest of chlorine's 7 outer shell electrons to be fully correct here. Perfect. So again, that's something we need to be a little bit careful of. So we need to, 1, make sure we're representing the covalent bonds in here, and 2, filling out the rest of the electrons in that outer shell. H2O, oxygen, group 6, so 2 covalent bonds. Hydrogen we've worked with quite a bit, we know it only needs 1. And again, we can get our structure drawn. Hydrogens, our oxygen, replace that line with a dotted cross. The hydrogen's electrons are all done, but this oxygen, we've only drawn 2 of its electrons. It's in group 6, so we need to draw another 4. Perfect. Carbon dioxide. So carbon, remember, needs 4 covalent bonds. Oxygen only needs 2. So this wouldn't work. We have double bonds. So this time, when we're drawing our dot and cross diagram, we have to do 2 lots of dot and cross to show we've got that double bonds. So we've got carbon, oxygen. We've got all of carbon's electrons. We need the rest of oxygens. Nitrogen, group 5, so needs 3 covalent bonds. So this will have, it's in group 5, so it has 3 covalent bonds. I thought I said 5. Anyway, so it will look like that, a triple bonds. So there we'll replace each of those 3 with a dot and cross. 2, 3. But there, each nitrogen only has 1, 2, 3 electrons. We need 5 in total. It looks like so. Lastly, C2H4. We've got our carbons, our hydrogens, but our hydrogens have all of their bonds. Our carbons only have 3 each, so we need a double bond here. This is ethene. Let's draw that. Brilliant. And these sorts of things really just require practice. So keep giving them a go, checking that you're right. Sci Sheets has some really good questions, although there is a bit of a paywall. Physics and Maths Tutor have lots of good questions as well. Now let's get on to the properties. So we get 2 different types of structure with our covalent. We get simple molecular or simple molecules, and we get giant covalents. So there we're going to again think about our melting points and boiling points, electrical conductivity, and we won't talk about solubility at this point, but we could do. So in terms of our simple molecular, this is our covalent bond, this is our atoms, and we also have what we call weak intermolecular forces between these molecules. So these weak intermolecular forces will hold the molecules together slightly, but only a small amount. So because of that, we have a low melting and boiling points. And this is important, our language here, as there are only weak forces between the molecules. Therefore, low energy to overcome forces. Couple of things there. If you say atoms here, they're going to think you're talking about the strong covalent bonds between the atoms. We need to be talking about these weak forces between the molecules, right? Next we come to and electrical conductivity. Absolutely not, because there are no charged particles. With our giant covalents, this time there are no weak intermolecular forces, right? It's not a molecule, it's a giant compound. This time all we've got is strong covalent bonds between millions and millions of these atoms. So here it's very high, as strong or as many strong covalent bonds between atoms in giant compounds require lots of energy to overcome forces. Let's move these down. And here again, no charged particles. But there are exceptions, so graphite. And that does have delocalized electrons. That's basically it. So, question I want you to give a go is, this is an A-level question about the structure and bonding here. Don't talk about magnesium, just explain why the melting point and boiling point of bromine is relatively low. I'll answer at the end of next video. For now, this was the question from the last one. So, room temperature, both sodium metal, sodium chloride are crystalline solids which contain ions. On the diagrams for some sodium metal and sodium chloride below, mark the charge for each ion. So is in group 1, so it's going to have a +1 charge. Now here for sodium chlorides, we're going to have alternating +1 and -1. So +1 from the sodium, -1 from the chloride. Perfect. Next, explain how the ions are held together, sodium and solid sodium metal. So here we've got strong attraction between positive metal ions and negative sea of delocalized electrons. To explain how the ions are held together in sodium chloride. So here we've got strong attraction a strong electrostatic attraction, sorry. Between oppositely charged ions. Again, I could have talked about electrostatic here, but we'll look at metallic bonding again later. The melting point of sodium chloride is much higher than that of sodium metal. What can be deduced from this information? Stronger forces of attraction. In NaCl. Next, compare the electrical conductivity of solid metal with that of solid sodium chloride. Explain your answer. Metal conducts NaCl does not. Explanation. So delocalized electrons in metal carry charge. In NaCl, ions are in a fixed position. Perfect. Hope that helps. See you next time where we'll look at metallic bonding. Like, subscribe. I'll see you then.